Hi, this is an introduction to modular form and modular functions. This is not an elementary introduction, but it's just to appeal to those people who are more familiar with geometric setting. So this is not the typical introduction people give, but in my opinion, it might be more interesting in this way for those people who know some mathematics, not this one. So it starts with elliptic curves. The elliptic curves Riemann surface of genus 1, and there's a way to construct elliptic curves using complex plane, and that attempt created this correspondence to all these elliptic curves they generate using the standard technique. Correspond each of the elliptic curve goes to the one point in the complex plane. And also they can reduce it so that that goes to complex plane and upper half plane. So this H represent for complex plane, upper half plane. Down there's a real line, and this whole thing, including the bottom part, supposed to be the complex numbers. And the next thing is the isomorphism class. E1 and E2 can be isomorphic to each other, whatever that means, and they translate that isomorphism relation into in here. If I have this E1 going to one point in upper half plane and E2 goes to another point in upper half plane, if they're isomorphic to each other, how does that translate in here? So this is their answer. So they define an action of this SL2Z as a 2x2 matrix with integer coefficients, integer entries, and its determinant is 1. And this action of this matrix on the upper half plane is this one. A T here is actually representing tau. So A tau plus B, it's a complex number divided by C tau plus D, and that's how it acts on the upper half plane. This is also called a linear fractional transformation, or called the Mobius transformation. We learned that in standard course of complex analysis. So if you have one point, and this is how the action is denoted, if you hit that complex point in the upper half plane by this matrix, and you obtain the gamma tau, and this particular one, it turns out is always in the upper half plane, and those two things correspond to isomorphism classes of elliptic curves. So that's something that interesting that is created on this very familiar space. It's upper half plane of complex number with this linear fractional transformation acting on that. So stories goes from here in this very simple setting that anyone who had very basic of a complex variables, complex numbers can understand. So we're going to forget about these isomorphism class of elliptic curves and focus about this very, very simple setting. And then at the end, we'll come back and come back to this connection and think about it again. But this is the very simple setting, upper half plane of complex numbers, and there's a linear fractional transformation acting on that. And we're going to identify 2 points in the upper half plane equal to each other if they're connected by the action of SL2Z. Right, this is a standard way of writing, identifying these points in upper half plane. They're connected by this SL2Z is considering these orbits, looking at this orbit as a one point. So orbits under this action is going to be denoted by this y parenthesis SL2Z, but later on we'll just simply write y and just focus on this simple setting. So first level is that this is simply a set and we want to turn it into topological space, And of course, this standard way is that you think about this obvious map. All these upper half plane is identified as one of the orbits in there. So H surjectively mapped into this set, and using this map, and we can induce a topology onto this space Y, which is a simply set. So that's a standard thing. So that's topological space. And can we visualize this one? All this thing is just definition in words, and here's one way to visualize what that topological space is. So this entire thing is upper half plane, and I'm claiming that all the other points in upper half plane is identified with the points in this vertical strip. Everything over here is going to be connected to that under SL2Z. Everything below this half semi-disk below that and can be moved up to here using the action of SL2Z. So I'm claiming that. But all the points inside is corresponding to distinct orbits. So Z-wise is 1-to-1. And this natural continuous map is created by this action preserve this homeomorphism for the interior. What's interesting here is this boundary, and the shifting by 1, this down there, it is saying -1/2 and +1/2. So if you add 1, you get in there. Adding 1 correspond to this 1, 1 here, and 0 and 1. Think about it as a 1, 1. That's tau plus 1, and 0 and plus 1. So that's tau plus 1. So tau plus 1 is one of the SL2Z action. So all the points here on this boundary is the same orbit as in the boundary in that space, topological space Y. So these two things identify. That's I'm using this arrow there. So what is happening underneath in here, using this -1 over tau, which is also some matrix, these half of this arc on the circle and the other half of this arc is identified to each other. So that's same orbit. So except the boundary, this interior is clearly showing this homeomorphic structure of this topological space it is created. So as a topological space, this Y, it is created by this interesting process. It just simply is this one in here. Next interesting thing is that that's how it is as a topological space, but we're going to enter the structure, that higher structure, it's a Riemann surface. And this particular Riemann surface created out of this process is called modular curve. But this is still like open topological space. So I'm going to add this word, an open modular curve. So modular curve is a compactified version of that. All right. Let me start it like this. Supposed to hide this. To identify this one, to give rise to this, to turn this one into Riemann surface, for each of the points in here, you have to give complex analytic structure, because it is constructed directly out of complex plane, and most of the part, giving complex structure is really easy. For example, if you're looking at this interior points there, any point, just take a small open neighborhood, there is a complex neighborhood, and that's it. Only thing you have to think about is this boundary, because you do not clearly see the complex open neighborhood around that point. So I'm going to start with a point on there, on that vertical line over there. So if we took a vertical line, think about just open neighborhood, small open neighborhood around that point, and realize and think about whether any of these 2 points same orbit under the action of SL2Z, then if it is all different orbits, then that gives you the analytic structure, complex analysis structure. Turns out all the points above that bottom points in there, you can easily see that. Not easy, you have to do some calculation, and it turns out they're all distinct orbits. So there it is. That's a complex analytic structure. So the problem spot is down there in the arc, and we're going to start with one in the middle there. That, as a complex number in the upper half plane, is the imaginary number I. So here's I. And it turns out if you just choose a small open neighborhood around there, turns out these points up there and points down there are not distinct orbits. So this whole thing cannot be an open neighborhood inside this open modular curve. It's because of this particular SL2Z element, 0, -1, and 1 and 0. And after applying an action, this corresponds to -1 over tau. Here tau is I. We're doing that to this one in there. Okay, so it turns out that particular SL2Z element fixes I in there. Because that Mobius transformation fixes it, what it does around that point, it's swirling around, give you like 2-to-1 map. So some of this thing, some of that thing, going to the same thing. So it's two things identified. So that's a problem. So we have to do something different to define or prove that there is an open neighborhood that can be turned into a complex analytic structure. So there's another point down there, the cusp point there. I mean, the shape is a cusp. Cusp is used for something else in theory of modular forms and modular functions, so I used the wrong word. So I'm just going to say pointy spot there. That's the point there. And if you just put a small open neighborhood, open circle there, turns out points up on these two pieces in here that belongs to that part and belongs to that part. And by the way, that point here is a third root of unity in upper half plane. These two parts, there's no, all of them are distinct orbits. But using one of the matrix, and this whole thing is rotated around there and rotated around there. So there are non-distinct distinct orbits around that neighborhood. So that's a problem as well. So you have to turn that one and analytically map that into an open neighborhood. So here's how they do. Let me just focus on one thing at a time. They introduce this particular action. This is not an SL2Z element. Look at first, these entries are not even in Z. But if you do whatever that, there's this particular SL2Z element that fixes this one, that caused this problem in there. Whenever that is the case, they apply this particular shape. If it is I and if it is different tau, and then you can put tau in, there's a negative tau. Down there is a conjugation of that tau. So if you do that, magically, it's turned that open neighborhood, because it's Mobius transformation, that's going to take the whole thing into a circle. But this is also part of the circle, and you know the Mobius transformation transform the circle into a circle or a straight line. If you just use a sample point, you can easily see that. Turns out it's this straight line. So that one in here, these are all distinct. If you just look at upper half of these neighborhood, they're all distinct, and they analytically transform to this nice one in here. And if you square that, you can see that close up nicely to the open neighborhood. And these thick lines, half of one here and half of one there, they're identified into the same thing. So under this very specific complex analytic map, turns this upper half of this neighborhood into a solid open neighborhood. So that part right there is now realized as a perfect open ball neighborhood. So that's why that has a Riemann surface structure locally there. All right, next one, use the same technique, whatever that matrix that fix is there. You apply this one instead of I, you put this third root of unity there. And then it turns out to be this piece in here. If you cube it, this is the pi over 3, I think. And then if you cube it, it closes up nicely into that. So that little piece there becomes the open neighborhood. Gives you complex analytic structure and a full open neighborhood in there. So that's why this Y here is a Riemann surface. Locally everywhere, it has this open neighborhood structure that is naturally constructed out of this complex analytic map. All right. Next thing they do, because there's this theory of a compact Riemann surface, there's a Rich theory developed there. So they want to turn this one into a compact Riemann surface, not open Riemann surface. So this is where it's opened up. So they have to compactify this direction of one point in there. So let's look at this direction. If you look at this as an the Riemann sphere, that's the North Pole, that one point compactification. To turn this one into a compact Riemann surface, you have to take this this direction in here all the way up infinite strip. You have to turn that into open neighborhood structure like that. And that's the goal, and it is done by the following map. If you look at this arbitrary truncation is somewhere higher in here, and this entire thing can be turned into an open neighborhood of a complex point. Their map is at e to the 2 pi I tau. I is turning around this one at 90 degree and putting in the exponential, and any horizontal strip putting the exponential under the exponential map that going into an open disk as a standard part in the one variable complex analysis. So if you throw in this 2 pi I, that reflects this period 1 nicely, and I together by this entire thing is mapped onto that 1-to-1. So what happens to these two vertical lines? They are identified same, and in space Y, they go to this particular horizontal line on the left side of this open neighborhood. So as this gun goes up to infinity, they go closer and closer to this center, which is not corresponding to any points on this strip in here. That is missing. It's a punctured open disk, and that corresponds to this additional point infinity that goes in there. And this bottom horizontal line, this one goes to the edge of this disk. So that's the correspondence. Gives you a little picture of how this one wrapped around into this open neighborhood. So that offers open neighborhood a complex analytic structure around this infinity. So that that additional chart gives you a structure of a compact Riemann surface. With this additional chart, we turn that into a compact Riemann surface. So that one is called Y, coming from the upper half plane, together with infinity. It's a compact Riemann surface, is denoted by X of SL2Z, but we're just going to use X in there as a one-point compactification. So I forgot what's next, what's behind down there. I think that's probably it. So yeah, so we have compact Riemann surfaces, and then we think about the Rich theory of a compact Riemann surfaces, and that naturally leads us to something called modular functions and modular form. But up until in here, all created by simple setting upper half plane, and the action of SL2Z created this interesting compact Riemann surface structure. Right, theories of compact Riemann surfaces. So let's review what those are. There's about something called Riemann-Roch theorem. That's what I have in mind. So what is this Riemann-Roch theorem? That's the central theory of the theory of compact Riemann surfaces. And they're about three objects. First, they think about meromorphic functions defined on that compact Riemann surfaces. Next thing, they think about differential forms on this Riemann surfaces, and all this thing is connected to the genus of that complex Riemann surface. So whatever that is, that's the three objects is involved in the conclusion of the Riemann-Roch theorem. So we're going to start with the meromorphic functions. Meromorphic functions are functions from that compact Riemann surface X to extended Riemann sphere, not just complex numbers. The infinity is thrown in there, so our poles are mapped to that infinity in there. So we have this map, and think about there's a projection from H star. H star is upper half plane together with that infinity we throw in. It naturally pull back the map to this entire upper half plane. So if you have nice meromorphic function, it creates a function from H star to C hat. So a meromorphic function from H star to C hat, that's what it creates. And next, this one is called pullback. If you have function in here, this composition gives you function structure on that bigger so-called covering space. Next one is this transformation property. Think about one point here, the orbit, and that corresponds to the multiple infinitely many points over there. They all should go to the same point under this composition. So we have the following interesting transformation property. If you're looking at tau in here and distinct point gamma tau as a point in upper half plane, they both go to the same orbit down there. Therefore, they go to the same function value. So if you pull back, meromorphic function defined on this modular curve, it creates a function in upper half plane, extended upper half plane, such that under this gamma action, they give you the same function value. So this is characterizing property, something called modular function. This function that satisfies this transformation property is almost called modular functions. All right. But there's this additional condition on infinity, because this is not only meromorphic at those points in y, that one more point we throw into this x, which we're just going to call infinity, the function is meromorphic as well, and we have to translate that to meromorphic property to the h star. This function got to be meromorphic at infinity. What does that mean? We need that open neighborhood structure. Not for the x, even for that one in here, h star. To define function being meromorphic, you need a full open neighborhood around that zero, around that infinity, and you can use that natural structure we use for that map, e to the 2 pi I tau. So if you think about this open neighborhood, this entire thing without that central point 0 is one-to-one to this vertical strip up there, and horizontally we have many copies if you want to consider h star as our domain, and the function is periodic in that because of, I mentioned that is tau plus 1 divided by 0 tau plus 1. That's what is it? That's the shifting by 1, and that's one of the SL2Z elements. So this function is invariant, so it is sufficient to consider in that open strip, because the function value here in that strip and function value in the next strip, they are exactly the same because it's invariant under any SL2Z action. So if you take that one vertical strip and transform it into that part, and define this composed map, meromorphic, to be meromorphic at infinity for function f that is have with the domain h star is a good sensible definition. So we have this f tau defined only on upper half plane and compose it and look at it as a function of q. Q is this e to the 2 pi I tau. Now if you look at this function in q, and that's the function defined around this neighborhood, now this g at 0 correspond to this infinity for f, so it is good definition. The definition of this f on h star being meromorphic at infinity is defined to be this function g as a function of q is meromorphic at 0. So that's the definition. But if you write it f of tau as a function of q and is meromorphic at 0, and this is the Laurent expansion, meromorphic means it truncates it in here, you write it like this. Now if you replace that q is e to the 2 pi I tau, and you can see this is exactly the Fourier expansion of this function because it has period 1. Again, the function is invariant under all the actions of SL to Z. That includes the shifting by 1. And this is precisely that Fourier expansion with a period 1. So if the function has this Fourier expansion as this Laurent expansion with a pole, that's the definition of this function being meromorphic at infinity. If you think about it, it's a really nice definition. I forgot that I wrote it down underneath it, but altogether, you can make a good sense out of this definition. So out of these meromorphic function defined on this Riemann surface, we created function defined upper half plane satisfying these two conditions. They're called autormorphic functions. All right. So that's the one thing. Out of meromorphic function defined on H, we have automorphic functions defined on upper half plane. Next item is differential forms. Differential one form on upper half plane. They're denoted by this capital omega 1x. And it is also known that if you have one differential form, all the other differential form is obtained by multiplying meromorphic functions on H. Right? So that's how these differential forms looks like. It's because of its dimension 1. So we're going to pull this one back to upper half plane again and see what kind of function what kind of differential one form we have on the upper half plane. Okay. So here's how it looks like locally, because using the chart, differential one form looks like meromorphic function multiplied by this dq, where q is that whatever the chart and q is centered at that point. We looked at various examples of that chart. So how it looks like, and because of that structure, locally pullback of this one, I think that's what I'm showing next, pullback of this one under the same connection, project onto x, and function is has to be c hat, gives you locally a function. I'm going to denote it by f subscript 2 tau d tau. The tau is upper half plane, so it creates this differential form on upper half plane H. And I'll explain why that 2, not 1, whatever that, where the 2 is coming from, is going to explain later. So I'm not going to go through the same type of discussion. It just gives you the pullback and think about transformation property. Once you have that differential form in upper half plane, and it should satisfy the obvious transformation property of this D thing. So for example, because they're defining the same differential form on X, if you look at gamma tau everywhere instead of this tau, it must define the same differential form. Okay, just like the idea of an automorphic function, and it gives you the same function value, it gives you the same differential form. So this gamma tau is given by this linear fractional transformation, and we're going to apply these Leibniz's rule to that d gamma tau to unfold this one and compare that with the d tau, then we kind of enter functions of upper half plane. So if you apply that to this d gamma tau, apply the quotient rule to that part, numerator turns out to be just 1 because of its determinant. The numerator turns out to be exactly the determinant, and the determinant is 1, and that gives you this 1 in there. And the denominator is a square of that part. So if you compare that in front of d tau, that's the function, and in front of d tau, that's f2 tau, whatever that differential, the meromorphic function that attached to this d tau. And these two must be equal to each other because this is local, and these two meromorphic functions to be equal to each other. So that gives you this strange condition. These two functions must be equal to each other. So f2 gamma tau is not equal to f2 tau, but when it's multiplied by c tau d plus d squared, then it's equal to each other. So if you compare that with the automorphic function, they're equal to each other after you hit it by gamma. This time it's not, but there is this factor. It's called Jacobi factor, and they're equal to each other. So this one is not called automorphic function because of that factor. It doesn't define on function, but it defines on differential forms. All right, any function that has this property will conversely define a differential form on this Riemann surface. So they focus on this interesting function. That 2 in the subscript came from that power exponent 2 in there. The question is, what kind of function is that? I might have forgotten to raise that question. It might have been in there. I think it disappeared, automorphic function. I think I forgot that question there. I originally had the question written there. No, I think it's coming back from there. I forgot where it was. Anyway, the question here is that can we find what are the automorphic function? It comes back later. I apologize about mumbling to myself. And here I'm asking the question, can we find one? I think I completely lost it. It's written somewhere in there. Where is it? The question I'm asking in here is that what are those functions? Do we have an example of that function? So there's one example of automorphic function for this SL2Z action, and that one I call F0. And here I'm asking the question, can we find one example that satisfies this condition? And if we have one example, all the other function that's this condition is coming from multiplying the meromorphic functions, that F0, and turns out all the automorphic functions that is considered here is generated as rational functions of that one particular automorphic function we found it in there. So what is that? Once you have that, if we find this automorphic form, not automorphic function, weight 2, that's what they call, and all the automorphic function of weight 2 is constructed out of that fashion. It's because of this structure right here. All the differential form is created by multiplying meromorphic function in there. All right, so I wrote it down. Any function that is defined in the upper half plane that satisfy this structure is called automorphic form of weight 2. And I forgot to write down this definition on infinity, but there is analogous definition on infinity in there. Forgot to mention. All right, that's the definition of automorphic forms of weight 2, and they also consider automorphic forms a higher weight. That's simply just changing that exponent to k and apply analogous condition on meromorphic condition on infinity, and gives you this straightforward definition of automorphic forms of weight k, and including the k being 0. All right, so that was my slightly unconventional introduction to automorphic functions of weight k for SL2Z, coming from more of a Riemann surface structure and considering the functions and differential forms. And these, if you push this one to the higher values of the k, it also has some meanings to going back to this Riemann surface, but this is a natural one coming straight from Riemann-Roch theorem. Next thing they do, they don't consider this SL2Z, they consider subgroups of SL2Z that has a finite index. And then going back all the way back, we do not have all the SL2Z elements, so this orbit's so-called fundamental domain, I forgot to introduce that name, this fundamental domain of the subgroup has a finite index to SL2Z, creates the bigger orbits, not the smaller one, as copies of this creates a different Riemann surface and creating a higher genus of Riemann surfaces. And then you can think about automorphic functions and differential forms and more, the same type of this transformation structure, not for all the SL2Z, but the SL2Z elements coming from the subgroup of SL2Z. I forgot to hide this, my face cam there again. So that concludes my supposed to be short introduction to automorphic forms and of weight k for SL2Z.